Hi, everyone. Thank you for coming to listen to the talk. My name is Omar Alrawi. I'm from Georgia Tech. I'll be presenting today the Betrayal at Cloud City, an empirical analysis of cloud-based mobile backends. This is a joint work between Georgia Tech and Ohio State. I'm a first co-author with Chaoshin Zhu. So imagine yourself at a conference and you're listening to a talk and you're really bored. Hopefully not this talk. And you pull out your mobile app to check in and get that killer seat you want on the flight back. And just as you do that, your airlines email you and tell you, oh, we're sorry, we just leaked your data all over the internet. It could include your name, your address, maybe your passport number, and definitely your credit card. But we take security very seriously. So you think to yourself, oh my God, why is this such a hard problem? British Airways is a capable company. They have billions of dollars of revenue. Why can't they allocate resources to solve a problem of securing my information? And that's a good question to ask, but there's more to it than what's on the surface. You see, the mobile apps we use are just the tip of the iceberg. To support all that experience, there's a whole suite of software that runs in the mobile backends. Starting at the web app layer, where APIs talk to mobile apps to serve content, serve ads, communicate telemetry back. And for this web app to run, you need software services like web servers, databases, and language interpreters. And to run all that, you need an operating system to manage the processes and the memory and the network stack. And of course, you need resources, virtual or metal. So you can see this backend is already a fairly complex ecosystem. So it's no surprise, actually, that we see a lot of these breaches hitting the headlines, with this article pointing to 21,000 Elasticsearch instances exposed and leaking 43 terabytes of app data. I mean, that's mind-boggling. Let that sink in, 43 terabytes. Another article points at third-party backends and how there are issues with developers being able to integrate with these third-party, and points to the problem, who should be responsible to address these problems? And this is not isolated to a single app or multiple apps or a handful of apps, but these are thousands of apps that are using reputable services like Google Firebase, which takes security very seriously. So obviously, there is some type of problem. So to understand that problem further, let's look at some prior work. Akar et al. Showed in their SOK in 2016 a trend for web apps being webified. And what that means is that the tip of the iceberg is shrinking and the base is growing. With the evolution of these backends, you see that not only data is being pushed down, but code is also being served to each custom device. And people have looked at the security of these backends. Several works have looked at the authentication mechanism between mobile apps and the backends. Some other works have looked at the integration between how mobile apps and cloud instances integrate. And App Authority has published countless reports of how serious this problem is getting in terms of leaks and exposures. So everyone meet Mil. Mil is a developer. This information is overwhelming to Mil. Mil just wants to ship a killer app. He doesn't want to think about what's underneath the iceberg, and even he probably is not aware of what's running under the hood or knows what operating system his app is running on. So how can Mil go about assessing the security of his mobile backend? There are a couple of challenges he must address. One, he needs to figure out what backends his mobile app uses. Two, he needs to check to see what security issues each of these mobile backends have. And once he identifies those problems, how can we go about fixing them? And finally, can he fix them? You'll see later that these backends are actually fairly complex in terms of ownership. So what we have done is we've implemented a pipeline called SkyWalker. And what SkyWalker does is it implements embodies binary analysis and backend security assessment techniques that allows Mel to assess his backend and answer these questions. So we don't want to interrupt Mel's development cycle. We don't want to interject and be able to do the security in the middle of his development. So what Mel does is compile his app and give it to SkyWalker to answer these questions for him. So how does Mel go about finding what backends his web app uses? Well, this might sound like a simple question, but Mel actually integrates with a lot of SDK backends, like Crashalytics, which provides crash and errors that happen on the device when the app is running. You have the Facebook SDK, which allows authentication or integration with social networks. And each of those is an iceberg by itself. Icebergs that come with their own problems. So what SkyWalker does is it applies static analysis, selective symbolic analysis, and dynamic analysis to extract request messages from each of these apps. So
we need some technical support.
Extract the request messages from each of these apps. I think we got it. Right. 1, 2.
Connection problem?
Yeah, just a second. OK, sorry about that. So that sounds like maybe a simple question to ask, because Mel develops his own app. So why would he not just be able to pull this? So what we found looking at the top 5,000 Google Play Store is that on average, each mobile app talks to at least 10 unique backends. And to put that in perspective, that means 10 different icebergs, 10 different backends with their own security issues, with their own set of bugs. So you can see how this can get fairly complex for a developer who has no security background. So once we know what backends we're talking to, how do we go about assessing these backends? It's a little bit tricky because each layer needs a special technique. For example, at the web app layer, SkyWalker takes the extracted request message, identifies the backend and the format of the message to the backend, and perturbs those inputs to find SQL injection, cross-site scripting, and external XML entity attacks, vulnerabilities. As for the rest of the stack, what SkyWalker does is perform a scan on all ports for each of these backends, identifies running services, and then fingerprints each service to identify what software is running on those backends and what version. Using that information, SkyWalker cross-references that with the National Vulnerability Database to identify issues that he can give back to Mel. So once we know all these bugs, how do we go about fixing these issues? And this is where it gets kind of tricky. So if Mel owns the whole stack, he runs his own backends from the hardware all the way up to the mobile app, then it's straightforward. All Mel has to do is take that list and apply it to each layer and fix those issues. But when he's using a third-party SDK, that gets a little complex, because now he doesn't have access to the backend. The only access he has is actually through the SDK. And then it gets even more confusing when we're looking at a platform as a service, because now Mel runs his apps, his mobile app and web app, but he does not own the rest of the stack. He rents it. So when a bug is discovered in the lower stack, he inherits a problem that he doesn't know about, and he might not be able even to fix if he knows about it. So how do we fix this? What SkyWalker does is takes several data sources and does data aggregation and consolidation, like who is data, geolocation data, and a curated list of colocation, CDNs, and cloud providers. And then labels each of these backends and provide a remediation list for each of those problems that SkyWalker finds. And that might sound like an overkill, but what we found in our analysis is that a lot of these networks are, a lot of these backends are running on diverse networks, and they're geographically distributed. So how can Mil, a developer, put yourself in his shoes, solve all these problems? So how effective is SkyWalker? So to answer that question, we unleashed SkyWalker on the top 5,000 apps from August 2018. And what we found is just over 600 zero-day vulnerability instances and over 900 end-day vulnerability instances in the mobile backends. To put things in context, the 0 days apply to the web app layer, while the end days apply to the lower layers of the iceberg. To give an overview of the type of vulnerabilities, you can see here that we found just over 1,600 vulnerabilities. 655 of those vulnerabilities are 0 days. 0 days. That means developers don't know about this, nobody knows about those. SkyWalker looked at over 9,000 different backends. And of those, I want to draw your attention to the third-party backends. Those are the most critical ones because those are shared between different apps. A bug there affects multiple applications, not a single application. In terms of the vulnerability types, you see on the operating system layer, we found a lot of backends running outdated OSs. And this might be expected. But the problem here, if a bug is discovered in any of these unsupported OSs, then the vendor will not be patching this, leaving the mill exposed to an attack. For the software layer, many of the backends use PHP. They were running outdated or vulnerable versions of the PHP interpreter. For the web app layer, the largest class of 0 days we found were cross-site scripting. And many people think or have misconception that cross-site scripting attacks are actually not very impactful. If you're attending the later talk this afternoon on the web attack track, I encourage you to attend the differential context vulnerability talk about pop-ups and iframes on Android. And you can link and see how vulnerabilities like this can be used to redirect mobile apps and install malicious software. In terms of the communication layer, many of them were running outdated or vulnerable versions of SSL version 2 and 3, which is known to be broken. So if you're doing any type of secure communication, resetting password, or perhaps exchanging sensitive information, we know that could be intercepted. In terms of the 0 days we found, I want to emphasize how effective SkyWalker is. In the top 116 apps in the Google Play Store, these have over 100 million installs and hundreds of thousands of reviews. SkyWalker was able to find 3 cross-site scripting bugs and 1 external XML entity bug. SkyWalker lives in our portal now, mobilebackend.vet. We offer this to developers to audit their apps and only their apps. For researchers, please contact us and we can give you access. So what's next? With all these bugs, we've been really engaged with the affected parties, trying to notify them of these bugs. Unfortunately, the response has been underwhelming. Even with 0 days and the urgency of identifying 0 days, we haven't been able to remediate everything. We have prioritized third party because those are the most impactful. If we address those, we will have a larger impact on the rest of the mobile apps. And finally, one area we are actively looking is trying to understand how these bugs affect apps on the device. How do they affect the users and how do they affect the device itself? SkyWalker has been inspired by many works. Here's a short list. And with that, I'd like to thank you for coming today. And I would like to open the floor for any additional questions that you might have. Thank you.
Let's thank speaker.
Hi, Ben from CISPA. Thanks for the interesting talk about the cross-site scripting. So I'm totally for cross-site scripting, but how can I exploit your mobile app? So I understand that there is a reflected XSS on the server, but how do I get my payload to you?
So this is one of the things I mentioned about the active area we're looking at, is trying to understand how you would be able to use this. That's why, and I also mentioned the work, the differential context vulnerability attack that will be presented in the web attack, showing how these type of vulnerabilities can be leveraged to be able to do bridging between the web view and the actual Java side of an app. So we're actively looking into this, trying to understand how it works, but we haven't really quantified it yet. It's very difficult because these devices and app usage are different for each app. Yeah.
Okay. Yeah, we can talk offline about this. Thanks.
So come to the Ben session in the afternoon.
Yeah, exactly.
Hi. So you mentioned the question of ownership, like PAS and third-party SDKs and all of that. But just wondering, is it OK to run SQL injection on third-party services without any permission or anything? How do you handle that?
So in the paper, we have an ethical consideration section that we highlight these issues and how we address them. If you want to talk about the technical details on what we did to
not so much technical. If I am the proverbial male and I want to scan my app, and because of the scan I end up crashing Facebook's infrastructure, and is this okay if I'm a third-party developer? What am I supposed to do in that case?
So you're talking about a third-party backends?
Exactly.
Yeah. So Facebook
SDKs,
and Google.
And some of them have SQL problems, and I scan my app, it runs the SQL injection, and the whole, let's say, Crashlytics goes down because of me. And how do you handle that?
So for our study, we've tailored the experience to empirically study it. In terms of individual app developer having access to SkyWalker, they'll be limited to their backends, because we already have a list of what third parties are. Okay. I'll give you an example from the paper. Like Unity 3D, we found a external XML entity bug in their backend, and we reported to them through Hack1. They acknowledged that. So many of those either run their own bounty programs. So with what's on mobile backend.vet, those will be limited to the infrastructure that the mobile app developer owns using the techniques we talked about in identification.
Okay, I see. Thank you.
You're welcome.
Hi, Tom Marr, Oracle. Thank you so much for this. I'm curious if there was any sort of independent auditing or validation that the CVs were actually applicable. Specifically, I'm thinking Linux vendors or distribution vendors frequently will backport patches and not update version numbers in like headers, as a specific technical example. So something may show up on a scan as vulnerable when in fact, no, the 0-day was patched by the vendor silently. Was there any kind of like treatment of that sort?
Unfortunately, we don't have insight into we don't have access to the backends themselves, so it'd be hard to verify that type of information. But based on some of the banner information, we'll have additional patches. For example, in Heartbleed case or OpenSSL, you'll see the patched versions. So we base that information based on banners, because we don't have insights on what's happening, what's have been patched and not on these backends.
So you're not trying to do like the Nessus or Metasploit approach of like actually exercising vulnerable code paths to see like, hey, is this a thing?
Yeah, we don't want to run any exploits on any backend that we don't own or have permission. So it's we limit it to the fingerprinting and correlation.
Thank you.
Yeah.
Thank you.
Thanks.
Okay, let's thank the speaker again.